Hello and welcome back to Math 220A, Mathematical Logic, Lecture 14, Presburger Arithmetic. In this section we study in detail a particularly nice set of axioms, the so-called Presburger Arithmetic, which is essentially the complete axioms for the theory of the integers z together with the constant symbols 0, 1, addition, subtraction, and the linear ordering. But, very importantly, no multiplication. If we also had multiplication in the structure, then this would be a structure in the context of the Gödel's incompleteness theorem, and we would know that there is no reasonable recursive axiomatization for the complete theory of the integers with addition and multiplication. However, it turns out that for addition alone, there's a very nice description of this of the axioms of the theory and a very nice quantifier elimination result. This also gives us a first example of a situation where, in order to obtain quantifier elimination, we have to expand the language of the structure. Namely, one can show that any quantifier-free formula phi of x in the language L consisting of the constant symbol 0, 1, plus, minus, less than. So for every such quantifier-free formula in a single free variable x, there exists a natural number n such that either we have that the structure z together with 0, 1, plus, minus, less than satisfies phi of n for all natural numbers n greater than capital N, or it satisfies the negation of phi of n for all n greater than capital N. So we see that every quantifier-free formula, the set of its solutions in the structure is either final or cofinal. In particular, formulas such as, for example, exists y, x is equal to y plus y, and exists y, x is equal to y plus y, etc. So these are the first formula defines the set of even integers, the second one defines a set of integers divisible by 3, etc. So these formulas are not equivalent to any quantifier-free formulas in the language L. So this can be verified as an exercise that every set definable in this language is either final or cofinal in this structure. And so this suggests that in order to obtain quantifier elimination, we would have at least to expand the language by some new predicate symbols for this kind of formulas. The important result of Presburger is that, in fact, this is all that we have to add to the language. Towards this purpose, we consider the language L-Presb for Presburger to be all the symbols from L, and we also add new unary predicate symbols P1, P2, etc. Next, we expand the structure on the integers to the structure z tilde with the underlying base set the integers, the constant symbol 0, 1, and addition, subtraction, less than, all interpreted as usual. and the predicate symbols pi are interpreted as z, 2z, 3z, etc. etc. So pi is interpreted in the tilde as the set I times z. So all the integers divisible by I. Then the structure z tilde satisfies the following set of sentences, which we denote as PRA for Presburger Arithmetic. So we have 1, the axioms of abelian groups, for addition and subtraction. Now the axioms expressing that the ordering relation is a linear order three for all x, y, z, x is less than y implies that x plus z is less than y plus z. So the operation of addition respects the ordering. 4, we have 0 is less than 1, and there does not exist y, such that 0 is less than y is less than 1. So the discreteness axiom for the linear ordering. Next, 5, for all x exists y, such that disjunction over all r greater or equal than 0 and less than n, we have x is equal to ny plus r times 1. For n, a natural number greater or equal than 1. So this is the axioms expressing division with remainder. So for each fixed natural number n, every element x can be divided by n with remainder. And finally, axiom 6, for all x, Pnx, if and only if, exists y such that x is equal to ny. Again, for every n natural number greater or equal than 1. So these are the axioms which define the interpretations of the predicate symbols Pn that we add into the language, that they express exactly divisibility by n. So these are the Presburger arithmetic axioms, and we're going to prove the theorem Presburger arithmetic has quantifier elimination. Proof: let phi of x1 through xn y be a conjunction of atomic and negated atomic formulas in the language LPresb By our early discussion of quantifier elimination, we know that it suffices to show that the formula exists y, phi of x bar y, is equivalent in PRA to a quantifier-free formula psi of x bar. We begin by trying to understand more explicitly what such a basic conjunction phi looks like. Claim 1. We may assume that each conjunct of phi is one of the following, so of the following form. For some m n natural numbers greater or equal than 1 and t of x an L Presburger term. So the possibilities are my is equal to t of x, my is less than t of x is less than my, or Pn my plus t of x. Indeed, every conjunct of the form my is not equal to t of x can be replaced by the formula my is less than t of x, or t of x is less than m of y, which is of course logically equivalent to the formula my is not equal to t of x. And then we can use the fact that the formula exists y, phi 1 of xy, or phi 2 of xy is equivalent to the formula exists y, phi 1 of xy, or exists y, phi 2 of xy. So the existential quantifier commutes with disjunctions, and hence the formula phi that we started with in disjunctive normal form can be modified so that every term of the form my is not equal to t of x using this equivalence becomes instead a disjunction of two terms of this form, but now only one of them occurs in any given conjunct of this formula, and so without loss of generality we only have to deal with one of the two. Similarly, a negation of the atomic formula Pn of my plus t of x can be replaced by the disjunction Pn of my plus t of x plus 1, or etc., or Pn my plus t of x plus n minus 1 times 1. Let us be clear here and throughout, we don't have multiplication in the language, so every term of the form my, or for example n minus 1 times 1, is just a term of the form y plus y, etc., m times, since m is a fixed number, not an element of the structure. And so we see that not being divisible by n is equivalent to having one of the remainders between 1 and n minus 1, which is exactly what this formula is expressing. And remember, this one of the axioms of Presburger arithmetic is divisibility with remainder. And so it remains to note that syntactically we have considered all the possibilities for the atomic and negated atomic formulas, where we managed to replace every negated atomic formula by one of the atomic formulas on this list. So this shows claim 1, claim 2. We may also assume that y appears, the variable y appears in every conjunct. Indeed, conjuncts in which y doesn't appear can be eliminated because we have the following universally valid sentence: exists y psi of x and theta of x y is equivalent to the formula psi of x conjunction exists y theta of xy. So we see that the question of finding a formula equivalent to the original formula with existential quantification over y is equivalent to finding a quantifier-free formula equivalent to the formula exists y theta of xy for any psi and theta, since this is already quantifier-free. This part is already quantifier-free by the assumption. Hence, from now on, we are assuming also that y appears in each of the conjuncts. Claim 3. We may assume that all conjuncts have the same coefficient m in front of the variable y. Indeed, since Presburger arithmetic implies that Pn of z is equivalent to Prn of Rz for any r, a natural number greater or equal than 1, we can replace a formula of the form Pn of my plus t of x by the predicate Prn Rmy plus Rt of x. Also, for r, a natural number greater or equal than 1, we can replace the formula of the form my is equal to tx by Rmy is equal to Rt of x, and likewise we can deal with the formulas of the form as my is less than t of x and t of x is less than my. So both of them we can also multiply both parts by r. The logical equivalence after multiplying by r is guaranteed by the axioms of Presburger arithmetic. So given a conjunction with potentially different mi appearing in front of the variable y in each of them, we can just take the common coefficient to be the product of all of the coefficients that appear, and using these manipulations we can change the formula to one which is equivalent in Presburger arithmetic and has the same coefficient in front of y in each of the conjuncts, which is the variable, the product of all of the coefficients appearing there initially. Now, using claims 1 through 3, and rearranging the conjuncts if needed. We may assume that phi of xy is of the form conjunction over h in h, my is equal to the term th of x, and conjunction over all I in I, ti of x is less than my, and conjunction over all j in j, my is less than tj of x, and conjunction over all k in k, p n k of my plus tk of x for some m natural number greater or equal than 1, h, I, j, k finite index sets, each n of k a natural number greater or equal than 1. Let us stress that some of the index sets hi, j, k are allowed to be empty, in which case the corresponding conjunction can be left out. So suppose first that h is non-empty, and say the element h prime is in h. Then the formula exists y, phi of xy is equivalent in Presburger Arithmetic to the following formula. So we have p m of th prime of x and the conjunction over all h in h, th of x is equal to th prime of x, and conjunction over all I in I, ti of x is less than th prime of x, and the conjunction over all j in j, th prime of x is less than tj of x, and finally the conjunction over all k in k, p n k of th prime of x plus tk of x. Let's see why this is true. Well, so by assumption, if h prime is in h, we must have that the corresponding term, th prime of x, is equal to my. This is expressed by the first conjunct. And the whole conjunction is satisfied if and only if all of the conjuncts are satisfied. Hence, we might simply replace every appearance of my in the formula by the corresponding term th of x, which is exactly what we've done here. And in this way, we obtain a formula without quantifiers, which is equivalent to the original formula, exists y phi of xy. So in this case, we are done. Hence, claim 4, we may assume that the set H is empty. So there are no conjuncts of this form expressing that my is equal to a term of x. Let us also remark that we stopped writing the bar on x bar everywhere, so that's assumed. So x and x bar denote the same tuple of variables x1 through xn. To understand the next step, we first focus on the standard model of Presburger arithmetic, namely the structure z hat with the underlying set the actual integers, although the argument that we provide works in any model of Presburger arithmetic. But first let's discuss it in the context of the usual integers. Fix any tuple A in Z to the n and consider the system of linear congruences with a known y. So we have the congruences of the form Pn of k of my plus tk a for each k in k. So k is capital K is a finite set. So we have finitely many conditions like this on y. Once the tuple A is fixed, which is more familiarly can be rewritten as my plus tk of A is congruent to 0 mod the natural number n of k, which again we have one condition of this form for each little k in the finite set capital K. Now, given such a system of congruences, we know that the solution in Z of this system form a union of congruence classes modulo the integer n, which we take to be the product of all of the nk for k in the finite set capital K. Since, of course, knowing the congruence class of an integer with respect to this number capital N determines the congruence class with respect to n of k for each k, where, as usual, we put n is equal to 1 for the case when k is the empty set. Now, observing this situation over the integers, this suggests replacing y successively by nz, 1 plus nz, etc. through n minus 1 times 1 plus nz, instead of just quantifying over y. So our precise claim suggested by this discussion is claim 5. The formula exists y phi of xy is equivalent in Presburger arithmetic to the formula theta of x given by the following expression. So we have a large disjunction over all r from 0 to n minus 1, where again the capital N is the product of n of k that appear in the formula. Then we take the conjunction over all k in k, p n of k m r times 1 plus tk of x and there exists Z such that we have the remaining conditions. So we have from the formula phi. So we have the conjunction overall I and I. Ti of x is less than mr times 1 plus nz. And we have the conjunction overall j and j, mr1 plus nz less than tj of x. So note that the quantified variable is no longer subject to the congruence conditions as we originally had in phi, since we can replace it by this new formula now. Proof of claim 5. Suppose that A with the base set A is an arbitrary model of Presburger arithmetic, and we have the tuple A consisting of A1 through AN from the base set capital A. Now we have to show that A satisfies exists y phi of AY if and only if A satisfies theta of A. So let B be an element of the base set A such that A satisfies phi of AB. Then division with remainder using the corresponding axiom of Presburger arithmetic yields some element C in the base set and some natural number R such that we have B is equal to R times 1 plus N times C, and the remainder R is greater or equal than 0 but less or equal than N minus 1. Note that then for K in K we have that MB plus TK of A is equal to MR times 1 plus NC plus TK of A is equal to MR1 plus MNC plus TK of A, which belongs to the set N of K times A. In other words, this element in A is divisible by N of K, and so we have that A satisfies P N of K MR times 1 plus TK of A, and I recall as usual that whenever we multiply, we don't actually have multiplication in the language. It just means an abbreviation for the sum corresponding number of times. And the data MR is provided by the formula. It's not an element of the structure. And so we have A satisfies this divisibility condition. And also we have that Ti of A is less than M R times 1 plus NC for every I in I. And we have MR1 plus NC is less than Tj of A for every J in J. That's of course because R1 plus NC is the expression for B in the structure, and we assume that B satisfies the corresponding formula. Hence, this holds as well. So, we conclude that A satisfies theta of A with the existential quantifier exists Z witnessed by C. For the converse, suppose that A satisfies theta of little a, and since theta is of course a disjunction of several formulas, at least one of the disjuncts must hold. So suppose the disjunct of theta of A indexed by R in 0 through n minus 1 is true in A with the existential quantifier exists Z witnessed by some element C in A. Then we can take B to be the element R times 1 plus n times C, and by looking again at the formula, we get that A satisfies phi of AB. Just unwinding the formula in terms of the original formula phi. So this shows that theta is equivalent to exists y phi of xy in Presburger arithmetic, since the model A in which we were working was arbitrary. Looking at theta, now we see that this part is quantifier free. So what remains is to show that this formula exists Z, etc., is equivalent to quantifier free one. So this means that we have reduced to the situation where H is equal to K is equal to the empty set. Of course, possibly after choosing the notation. So this means that in our formula there are no equations and there are no congruences. So we only have the inequalities part, i.e. phi of xy is of the form conjunction overall I in I, ti of x is less than my, and the conjunction overall j in j, my is less than tj of x. In the case when j is empty set or I is equal to the empty set, then we have that Presburger arithmetic implies exists y phi of xy. Indeed, assume, for example, that j is equal to the empty set. Then we are only concerned with the family, finite family of inequalities given by all I and I. But then we would have that for any A models Presburger arithmetic and a tuple in the base set of length n, we can consider the set T1 etc. So the set Ti of A for I in I is finite, so just a finite set of elements in the structure. But of course, the underlying linear ordering of the structure has no largest element. So we can always find some B which is greater than all of the elements of this set. So if we call this, for example, T, some B in A, which is greater than all of the elements in the set. So of course also MB is greater than all of the elements in the set. And so A satisfies phi of AB for any choice of the tuple A. So indeed, Presburger arithmetic implies exists y phi of xy in this case. The case when I is empty is symmetric. Just have to pick an element smaller than all elements in a given finite set. And so, by our convention on quantifier elimination, in this case we see that Presburger arithmetic implies exists y phi of xy if and only if x is equal to x. So we obtain a quantifier-free formula equivalent to this. Hence we have claim 6. We may assume that both I and j are non-empty. Now let A be a model of Presburger arithmetic with the underlying set A. Then for each choice of tuple A in A to the n, there is some I0 in I, such that the element Ti0 of A is maximal among the elements of the form Ti of A with I in I. And also there exists J0 in J, such that Tj0 of A is minimal among the elements Tj of A with J and J, simply because both are finite sets. So we can choose one which is maximal and one which is minimal. And moreover, each interval of m successive elements of A contains an element of MA, so contains an element divisible by M. This just follows from the axiom of Presburger arithmetic. Therefore, we have that the formula exists y phi of xy is equivalent in A to the disjunction over all pairs I0, J0 in I times J of the quantifier-free formula given by the following expression. So we have the conjunction over all I and I. Ti of x is less or equal than Ti0 of x, and conjunction over all j and j, tj0 of x is less or equal than tj of x, and conjunction overall R from 1 to m, Pm of ti0 of x plus R1 and ti0 of x plus R1 is less than tj0 of x. So namely, since we always know that in any interval long enough, namely an interval of m successive elements, there exists an element divisible by m, then exists y phi of xy, which expresses a number of linear inequalities with coefficient m, indeed can be written as this the disjunction over all pairs I0, J0, because we don't know in advance for a given A which Ti and which Tj0 are going to witness the maximal and the minimal elements respectively, but there will be some choice for which they will be the maximal and the minimal one, and hence for that choice the corresponding disjunct is going to be satisfied. And of course, if one of them holds, then the formula exists y phi of xy also holds. So this completes the proof. Note that whenever we write less or equal in this expression, of course, it's not part of the language, so we use it as an abbreviation for the formula t is, so if we write, for example, t is less or equal than t prime, this is an abbreviation for t is less than t prime, or t is equal to t prime. Okay, so this completes the proof of quantifier elimination in Presburger arithmetic. Immediate corollary: the theory Presburger arithmetic is complete. Proof: it satisfies quantifier elimination, as we just proved, and moreover, the standard model z tilde, which is the integers with addition and divisibility by n for the predicates Pn, embeds into every model of Presburger arithmetic. So namely, we can just look at the interpretations of the symbols 1, 1 plus 1, 1 plus 1, etc., and also their inverses. So this gives us a copy of z tilde inside of any model of Presburger arithmetic. And then we know by the general criterion for completeness of a theory that Presburger arithmetic is a complete theory. Note that unlike the case of algebraically closed fields, we have not used the semantic criterion for quantifier elimination here, but rather were really explicit about how to obtain a quantifier-free formula equivalent to a given arbitrary formula. So this elimination procedure that we presented here is constructive. It actually describes an algorithm which allows on an input basic conjunction in the language of Presburger arithmetic, outputs a quantifier-free formula equivalent to it in Presburger arithmetic. This can be used to, for example, deduce decidability of the theory of Presburger arithmetic, and sometimes this is called effective quantifier elimination. But this will be a topic of the second part of this course, 220b, so we won't focus on this in detail here. Thank you very much for your attention.